vlog. This is section 4.4, Media Access Control. My name is Jasmine. I am the vlogger. My topic is 4.4.1 topologies.
My name is Josh. I'm the gamer. I got 4.4.3. Now I have LAN topologies.
My name is Caden. I'm the questionnaire, and I'm doing 4.4.4 data link frame.
My name is Matthew. I'm the summarizer, and I'm doing 4.4.2 LAN topologies.
I hope you enjoy our vlog. See you in 2 seconds.
1,
2, 3. Hello, I am Jasmine from group 4.4. My section is 4.4.1. So, the Media Access Control sublayer controls the arrangement of data frames upon the media. Topology and media sharing help determine the media access control method. The topology displays the positioning of the network devices, portraying how they are correlated. Physical and logical topology are the ways that LAN and WAN topologies are perceived. The data link layer controls data access to the media while watching the logical topology of the network. Here are the displays of the topologies. Here is an example of sharing the media. The computers know that they need rules for how to share the media. Here is an example of a physical topology.
She's looking for more questions. Use your own computer or use a computer now.
Here is an example of a logical topology.
Need a question, John. Need a question.
Whoa, I thought I saw something. Is that? It is! The Cisco class! Well, since you guys are here, I might as well talk about my section, which is WAN topologies, a part of the 4.4 group. So if you'll keep listening, I'll begin now. Hi, Cisco class. So, professional. So my computer had a question for me, which I will answer right now.
What is a physical WAN topology, Matthew show?
Well, a physical WAN topology, it's a wide area network topology. It describes the layout of a network's components and connections on a given WAN. Well, Siri, does that answer your question for you?
Not really. What do they look like? What are the common topologies?
Well, there's the hub and spoke, the point-to-point, and there's the full mesh. Basically, the point-to-point sounds kind of what you think. There's a point and there's a point. It's the simplest topology, and it is a permanent link between two endpoints. So it's very popular. Then there's the hub and spoke, which is the star version of the WAN, and there's basically the branch in the middle, and then there's the branches around it. Then there's the full mesh, and so for a full mesh WAN topology, each link is essentially a point-to-point link to the other node. A full mesh topology relies on every site's WAN router having a connection to every site on the wide area network. Full mesh topologies provide a high degree of dependability and fault tolerance, but this comes at a heavy price. This is a point-to-point topology. Here we see it's directly connected to a node. See that? Yes. Here we see with the logical point-to-point topology, these are logically connected, meaning it's indirectly connected over a geographical distance via a virtual connection. So, Siri, how was that? Honest.
Oh, thanks for that. Very informational and 100% worthy, wink wink. But don't you have the APS history homework to do?
Whoa, you're absolutely right, Siri. I bet I should get on that. Maybe we can go to Josh's video. This video was sponsored by the Brotherhood of Cisco. In Cisco we trust.
Hi, my name is Josh. I'm doing land topologies 4.4.3. So let's get right into it. Physical land topologies. Let's talk about the star. All the end devices in a star all connect to a switch. In earlier days, they used to connect to a hub, but now we do switches. And they're very easy to install and very scalable. Very easy. And easy to troubleshoot too. So there's some positives about that. And we got an extended star. Basically, what an extended star is a star, but it connects other stars together. That's basically what extended stars are. And then we got the bus. This is where the end systems are chained together and terminated at the end. So basically, they're easy to set up. They're very inexpensive. That's what buses are. As you can see here on the left, they're terminated on the end. They're easy to set up. And ring is different from a bus, but it's different from a bus. It doesn't need to be terminated, and they're connected to their respective neighbor, forming a ring, like the ring that you have on your finger, ring that you wear. Kind of looks like that. All right. Next, we have half and full duplexes. So these are pretty simple. Half duplex, you can send and receive, but you can't do it at the same time. So basically, like a walkie-talkie, you can talk into it, and other person receives, but the other person cannot speak at that exact same time. They have to wait until you let go of that button. And that's and in networking, that can cause major slowdowns because you have to wait until your message is sent across the network before you can send another one. And that can be very, very frustrating because the network is slow and your message can't get across. Alright, full duplex communications. So basically both devices can send and receive at the same time. Well, yeah, at the same time. That's the difference from half duplex. It can send and receive at the same time. But it can cause interference like crosstalk. And no one likes crosstalk. But it doesn't slow down the network because you don't have to wait for someone else to send a message so that you can send a message. You can just talk. Alright, now we have... So, there are two kinds of media access control methods. Contention-based access and control-based access. So in contention-based access, all the nodes are operating in half duplex. So, only one device can send at a time. And that's bad because if you have multiple devices on a network and if only one can send, all those other devices have to wait. That's not okay. And in controlled access, each node has its own medium. And that's very insufficient because each device has to wait its turn to use the medium. And that can also slow things down on the network, and that's not okay on a network. Everything should be efficient, not inefficient. So, and then next we have contention, and then we have CSMA/CD. CSMA/CD. So what this is, if two devices send at the same time over the network, it will crash. A collision will occur. So both devices will have to detect that collision on the network. And that message will be corrupt and it will have to be resent over the network again. That's what that is. CSMA/CA, or crash avoidance. Crash avoidance. So basically what this is not like crash detection. Well, it kind of is like crash detection, but it avoids the crash. It waits until that message is sent, then it sends the message. So this is what It's kind of like on a highway when you wait for someone to make a turn, then you go. Yeah, it's kind of like that. You're avoiding the crash from happening. That's CSMA/CA.
Hey y'all, welcome to my section of the vlog. So today we're going to be talking about the data link frame. So first off, the data link layer is responsible for preparing a packet for its transport across the form of local media by encapsulating it with a header and a trailer to create what we know as a frame. This frame is a key element of each data link protocol and contains the three basic parts: the header, the data, and the trailer. The structure of the frame and the fields contained in the header and trailer vary according to the protocol specifications. It is true that there is no one frame structure that is able to meet all the requirements of data transportation across all types of media. Depending on the set environment, the amount of control information required in the frame varies in order to match the access control requirements set forth by the media and logical topology. The figure here in 4.4.4.1 displays how more controls are required to ensure delivery in a fragile environment. Framing breaks the data stream into sets of decipherable groupings, having control information inserted in the header and trailer as values in different fields. This format is able to give physical signals a structure that can be received by network nodes and later decoded into packets upon reaching the destination. Some generic frame field types include frame start and stop indicator flags, addressing, type, control, data, and error detection. Data link layer protocols add a trailer to the end of each frame to determine if the frame has arrived without any apparent error. This process is known as error detection and is added at the data link layer due to how signals on the media can be subject to interference, distortion, or loss that would change the signal's representation. Here in this activity, we have a frame that shows us the header and trailer fields. What we will have to do is match the fields with their location in a generic frame. Here in this activity, we will be matching the field names with their proper description.